Oh, okay. And so, welcome everybody. Yizhar Or from mechanical engineering. The program is called Autonomous Systems and Robotics, right? So I'm more inclined to the side of robotics and more to the mechanical side of robotics, but robotics is multidisciplinary. It has multiple facets, so it also has interface with computer science and engineering and integration of systems. So the core of my work is nonlinear dynamics and mechanics of underactuated robot locomotion. Locomotion is the ability of any robot to generate some thrust and generate some motion. Very basic, like toy-like mechanism, like crawling. And this is wheeled robots, but the wheels are not actuated. The wheels are actually free, and it's moving by changing the joint angles. Here it's articulated robot. It's like a snake crawling. And I have some more specific topics related also to courses, advanced courses that I give in the graduate program. Also, I think appear in the list of TASP, right? So I will have a slide on courses. One of the courses is hybrid dynamics. Obviously, when there is naked robots that is working, it's not just a simple dynamical system. By the way, I didn't include any equation here. I think there was a specified quota and it was ran out by all these guys, but I will write a single equation if I have okay. A single equation, okay? I try to make it large. Something like this. It's a differential equation. State equation. X is the state vector. If you studied anything with linear or nonlinear dynamical systems, it's a nonlinear dynamical control system because this is the vector of controls that we can control and describe them, and this can describe the motion of a robot, and this can describe forces or any actuation which we can try to minimize, and we are trying to drive this solution of this system to a desired trajectory, to some desired motion, and optimize the motion. That's basically the simple equation that is related to almost everything, except that if I'm a walking robot, it's more complicated than that because I have a switch between different states of the contacts. A leg is hitting the ground and then it's touching the ground. It might be slipping or sticking on the ground. So I have hybrid dynamics with multiple frictional contacts for legged robots. Some of these robots are just undergoing some periodic actuation, and then it's very interesting to do asymptotic analysis. So we can do toys moving and we can do system integration, but we can also do very heavy math of this, do asymptotic analysis for such systems. I will show swingers in the next slides, soft robotics, robots which are deformable, in which we try to do minimization of the control inputs. I have one, actually it's called a flagship project in TASP, in autonomous system, which is led by me and Amir Gat, and some other Amir Gat and Oren Zaltzman and Amir Gani. So we have some projects which are jointly supervised. I have also collaboration with Professor Shai Rebson from the University of Michigan. I think more suitable to electrical engineering, computer science engineers, data-driven models for rhythmic robot locomotion. I will show in one of the next slides. These are some swimmers. These are swimmers that we built in the lab. Even I have one swimmer swimming in Alex Liberson's swimming pool. I don't know if you remember this. One of the swimmers. In Dan Liberson, sorry. Alex Liberson is from Tel Aviv, sorry. Okay. And this one is on the centimeter or even meter scale. This one is micrometer scale. This one is in Zurich, and it's actuated by some magnetic field. It's under microscope here. And we are writing equations like this and analyzing how we can control this robot and improve its performance. Nonlinear dynamical system. Legged robots, a collaboration with Caltech on working on the treadmill. This is a very sophisticated robot, and the trick that we did is that we put oil, lubricant, on the treadmill, and the robot existing algorithm just fails to walk. It just is unable to complete a single step. But if we adapt our control algorithm to account for the friction limitation and to account for the switches between sticks and slip states of the foot, then it can work on different speeds and different coefficients of friction very robustly. So it's a toy, but the math behind this is hybrid dynamics and nonlinear control. And this is for soft robotics, robots with a flexible structure that we are trying to control them with minimal actuation. You can see these are fluid driven, it's a fluid inside some tube, some zigzag channel inside the solid elastic beam. Here it's something which is like a straw. A straw is something which is multi-stable. It has multiple stable states, and we can move it between stable states by some actuation. Here it's just inflation and deflation of fluid, but it can be something else. Here we have things which are, each element like this is bistable. It's like this hair clip dumping between two stable states with very minimal actuation. So it's like a binary machine that we can move it between different binary states. And here we show that we can do it with a single input. With a single input, we can control it between 2 to power n elements states in a prescribed way. Again, by dynamics, which is somewhat reduced to this form of equation. And this is the flagship project of autonomous multi-stable robot for search and exploration, jointly with Americani or Zaltzman. Here it has parts of system integration, of actuation. It's also motion planning. This is like a strong-like robot with minimal internal actuation. There is a single internal robot that goes inside this strong-like pipe and changes its degrees of freedom by bending, extending, or contracting back with a minimal actuation. So it has components of motion planning with Oren Zaltzman, that's his expertise, and components of estimation, of cause estimation, which will be with Amir Gani.
Walton is presenting the poster outside.
That's one of the posters. In some cases, we don't know the model because it's too complicated. It has multiple legs, or it's moving granular material. Even fluid mechanists can admit that granular material is complex interaction, complex equations. So we don't know the equation. We assume some simplistic structure, and we try to learn some model by taking data-driven, taking measurements. We have measurements, and we can fix a model and learn the model in order to control the system. This is something jointly with Shai Revson from Michigan. We need people with good background also in computer science, in data processing, in statistics. I think that's without movies. And these are the two relevant courses, relevant also to this equation. I'm now giving in this winter, this spring, kinematics, dynamics, and control of robots in English, but also Hebrew friendly, and hybrid dynamics in mechanical system. Hopefully next winter will be done again. I think both of them, I don't know, don't ask me what list, ABC, but because I don't know, but they are all in the semi-elective list of autonomous systems. I think that's it. And now the dessert after the dessert is the coffee.